Units of measurement. Units are really, really important. Back in 1999, the Mars Climate Orbiter was supposed to be orbiting Mars and taking samples and readings and stuff. It cost $125 million. It didn't do what it was supposed to do. It got too close to Mars, got pulled into the gravitational force, and crashed. Gone, lost. The reason that this spaceship was lost is there were two different teams of engineers who failed to communicate about what units they were using. One team was using English units, one was using metric, and there was a screw-up in putting the stuff together. Okay, your mess-ups with units will not cost $125 million, but units are important. I know it's just a little detail, but details matter. Okay. There are two common unit systems, the metric system and the English system. Here in the United States, we're just clinging on to the past and using the English system. Most of the rest of the world uses the metric system, and it's really a much better system. Scientists use the International System of Units, or the SI system. The SI system is based on the metric system, and in my opinion, the differences between it and the metric system are not really even worth talking about. So I will tend to use metric and SI system interchangeably, but I'm telling you right now there are very subtle differences. So these are the base units in the SI system. We're not going to encounter all of these in this class. We're going to have length. Oh man, stupid thing. My stylus is acting up still. It started this yesterday. We're going to deal with length, mass, time, temperature, and amount of substance. So meters, kilograms, seconds, and kelvins. There's more information on these slides than you need to know, but I think some of it's just kind of interesting. What I want you to know is the rough size of a meter. A meter is just a little bit longer than a yard. So this is a meter stick. There's a picture up there as well. A meter stick is 39, it's like 39 and a half inches. A yardstick is 36 inches. So very similar in size. The reason it's important to have just a ballpark idea of how big these units are is because then when you calculate an answer, you have a clue, is this a reasonable answer or not? If I measure the height of my little dog Churro and I come up with him being 3.7 meters tall, is that reasonable? No, that's not even reasonable for a human, much less a little crazy dog. Okay, so 37.37 inches. You don't need to memorize that. Mass. We measure mass. Mass is how much matter is in this object. It's the quantity of matter. We're more familiar with weight. Weight is actually a measure of gravitational force. If you're staying on the same planet when you're doing this, then you can use mass and weight interchangeably. Anybody planning to leave the planet during this semester? I thought about it. You thought about it? Yeah. Okay, well then you guys might have some issues with this, but the rest of us will be fine. SI unit of mass is a kilogram. A kilogram is about 2 pounds. So it's in the same ballpark as pounds. The more common unit to be used in chemistry is a gram. A gram is a 1/1000th of a kilogram, and this is helpful. They've put a nickel on this balance. A nickel, which is 5 cents, weighs about 5 grams. So that gives you an idea of how big a gram is. It's pretty small. Time is measured in seconds. This is the same second that we use in, well, how long could you hold your breath? That many seconds. All of these units have very, very precise definitions. I didn't read the other two, but the second is defined as the period of time it takes for a particular number of radiation events of a specific transition in cesium-133. They've defined this Second, in that way, because people in different places can all come up with the same size unit. And you don't need to know those definitions. Kelvin is the SI unit of temperature. We'll talk about kelvins in just a minute, but let's talk about temperature right now. So temperature measures the average kinetic energy in a substance. Even solids have kinetic energy because the particles are moving. They're just not moving relative to each other. So you guys all have some kinetic energy right now. It's just that you're not running around. But you're breathing and scratching your head and taking notes and different things. If you put energy into a substance, you increase the kinetic energy of the particles and they wiggle faster. Think of, a group of kindergartners, you feed them sugar and now they start fidgeting and wiggling and they're having a hard time sitting still. Temperature gives us a measure of the average kinetic energy. It also predicts or determines how thermal energy is going to be transferred from one thing to another. Thermal energy always goes from the warmer substance to the colder substance. You put an ice cube into a cup of room temperature water, and the same thing always happens. The water gets colder. It was warmer to start with. The thermal energy from the water gets transferred to the ice cube. The ice cube warms up and melts. It never happens the other way. You can't put an ice cube in a cup of water and have the water get hotter and hotter and the ice cube grow and get colder and colder. It just doesn't happen. So these temperature scales, the Kelvin scale, you should have heard of that in your previous chemistry class. What we're familiar with in everyday life, what the weatherman uses, is Fahrenheit. A lot of the cooking recipes, 350 degrees, they mean Fahrenheit. So the Fahrenheit scale has water boiling at 212, water freezing at 32, and in between is 180 degrees. This scale was come up with a long, long time ago. The centigrade or Celsius scale, Celsius is the preferred term, bases itself on the freezing point of water being 0 and the boiling point being 100. And then there's 100 degrees in between. So between Fahrenheit and Celsius, the units are different sizes and 0 is in a different place. And then the Kelvin scale uses absolute 0 as its 0. Question?
Why the US system? They come up with 32?
Yeah, how did they come up with 212 and 32? It turns out that the guy who established the Fahrenheit scale, 0 Fahrenheit was the coldest temperature he could get from a saturated salt solution. So he was looking for something that could give the coldest reproducible temperature. So when something is in the process of melting or freezing, it stays at the same temperature. So if you take saturated salt solution and you cool it down and you cool it down, it will stop at its freezing point, and that would be 0 degrees on the Fahrenheit scale. I think 212, actually I'm not sure where he came up with 212, but there is a story behind it. I know the 0 part, but it's kind of silly. So the Celsius scale also, it's like, well, what do we call 0? Well, practically, it's easy to establish a temperature of 0 degrees Celsius. So, my ice all melted. I had ice in this. When there was ice and water mixed together, I know that the temperature of that is going to be very close to 0 degrees Celsius. Anytime you have ice and water together. If I boil pure water, I know that it's 100 degrees Celsius. And so somebody could just use freezing water, boiling water, and make their own thermometer. And back in the day when, people had to make their own instruments, this was a big deal. The Kelvin scale, you might wonder, well, 273, what the heck? Why do that? this is based on a concept of absolute zero, that there is an absolute lowest temperature below which nothing can go. And the theory is that at absolute zero, motion stops. So you take a solid object, it has kinetic thermal energy because the particles are moving. As you cool it down, the kinetic energy of those particles gets lower and lower and lower, and when they stop moving, that's absolute zero. No one has attained absolute zero, but they've gotten incredibly close. I looked it up the other day. They've gotten really, really close. So the Kelvin scale versus the Celsius scale, all that we've done is move the 0 point. There's 100 kelvins between water freezing and boiling, 100 degrees Celsius. The size of the unit is the same, it's just offset. So on the Celsius scale, again, based on 0 and 100, I kind of said all that stuff. So here's the important stuff. Equations. We're going to talk about dimensional analysis today and unit conversions. Temperature conversions are a situation where you have to use the equation. You have to use an equation to convert from one to the other. So you need to memorize these equations. Those equations are in your textbook. The slides and the handouts are posted on Blackboard. Here, let's do an example. Gallium is a solid metal at room temperature, but if you hold it in your hand, you can get it to melt. It's pretty neat stuff. Unfortunately, it's kind of toxic too. The melting point of gallium is 85.6 degrees Fahrenheit. What is this temperature on the Celsius scale and on the Kelvin scale? So they're giving us 85.6 degrees Fahrenheit, and they're asking us to calculate the temperature in Celsius and in Fahrenheit and in Kelvin. So this problem is requiring two different answers. The first part is we want to take 85.6 degrees Fahrenheit and change it into degrees Celsius. We need an equation to do that. It was on the previous slide. Degrees Celsius equals the Fahrenheit temperature minus 32 divided by 1.8. So we're going to stick the number in there, 85.6. I'm going to subtract 32. Get your calculator out and do this. You want to make sure that you finish that subtraction before you divide. Otherwise, you'll end up with 85.6 minus 32 divided by 1.8, and that's going to be different and wrong. So what I do is 85.6 minus 32, and then I press the equals button to say finish the subtraction, then divide by 1.8. And I'm going to write down most of what my calculator shows me. We're going to also cover significant figures today. So it just goes on and on and on and on. And the unit there would be degrees Celsius. We're going to talk about rules for sig figs. There is a shortcut for temperature, and so I want to tell you about that right now. And if you're interested in why, ask me in lab and I'll explain it to you. So look at your original temperature. This is measured to the tenths place. It has its last digit in the tenths place. So then I want to take my converted temperature and round it to the same place. I want to round it to the tenths place. And so I should report this as 29.8 degrees Celsius. That's pretty easy, huh? There's no counting sig figs or doing anything of that yet. You just round it to the same decimal place as the temperature you started with. Okay, so for part B, we need to go to Kelvin. You could come up with an equation that would convert Fahrenheit to Kelvin, but since we do that so rarely, It's not in the book. I don't know what it is off the top of my head. So if you had to go from Fahrenheit to Kelvin, you would convert from Fahrenheit to Celsius, and then convert from Celsius to Kelvin. So we already did the first part of that. When we're taking a number, so we already did a calculation to get this. If we're going to continue on and use another operation on it, I'd rather start with this number that hasn't been rounded at all. And I'll explain that kind of idea later. So Kelvin equals degrees Celsius plus 273.15. So I'm going to take that 29.77777, a whole bunch of sevens, plus 273.15. I still have that number in the display of my calculator, so I'm just going to add 273.15 to that. I'm going to get 302.92777, blah, blah, blah. In rounding this number, again, I'm going to look back to the number I started with. This had 1 decimal place. It was to the tenths, and so I want to round this to the tenths as well. I'm going to keep this 9, and I'm going to say it's 302.9 Kelvin. The unit is Kelvin, abbreviated capital K. There's no degree sign. Fahrenheit and Celsius are degrees Fahrenheit, degrees Celsius. This is not degrees Kelvin, it's just Kelvin. Any questions? So the metric system uses prefix multipliers. Oh, I jumped ahead. First line here. See Appendix 1A for a review of scientific notation. I'm going to assume that you know how to do scientific notation. If you don't, read the review. If you need some help, ask me, and I'll talk to you and explain it over again. We use prefix multipliers to change the size of the units. We need different sizes of units. I live in Reedley. I work here in Fresno. How far is it from my house to Fresno City College? What kind of a unit would I use? Inches? Feet? Probably miles, right? It's roughly 30 miles. I really should clock it someday. I think it's like 26 or something. I wouldn't measure it in inches because that would be this ridiculously huge number, and it just really wouldn't be all that meaningful. We like to use units that are similar in size to what we're measuring. If you measure the height of a person, you're not going to use miles because that unit is way too big. You're going to use feet, maybe feet and inches. Okay. So in the English system, we have all these units. We've got the inch, and there's 12 inches in a foot, and there's 12 feet in a yard, and there's 5,280 feet in a mile. And they all have these different relationships. And some of them are hard to remember. In the metric system, everything is powers of 10. And there's a set of prefixes, and the same prefixes are used on all the units. So on the list of stuff to memorize for the memorization quiz next week is a list of metrics prefixes, and metric prefixes, and their meaning. And so you memorize those, and then you're good to go on metric conversions. Kilometer is a prefix. Kilo is a prefix. It means 1,000 or 10 to the third. So that makes the unit larger. 1 kilometer is equal to 1,000 meters. Another way of writing that is 10 to the third meters. So these are the metric prefixes, the metric multipliers. Memorize the ones that are on the list I gave you. I don't know if I put all of them on there or not. The most important ones are kilo and centi and milli and micro. Those are the ones we use most frequently in chemistry. So you need to memorize the name, the symbol, and here capitalization counts. Capital M is mega. That makes a unit big. Big M makes it bigger. Small m is for milli, and that makes it smaller. We ran out of m's. We also have micro. So micro is the Greek letter m, mu. If you look at these multipliers, those are lots of zeros. I can't just remember all those zeros. I think memorizing the factors here with the exponents is much easier. Most of them are powers of 3. So here this is minus 3, minus 6, minus 9, minus 12, minus 15. We're counting by threes. Just a couple here in the middle that are different. Examples. There's a couple of problems on the worksheet we're doing in lab today that are going to ask you to do things like this. And this is so simple that it makes it difficult. So we're just trying to get you to understand, what does the prefix do? What does it mean? So if we ask, how long is 4.5 megameters in meters? All we have to do is stick in what mega stands for. So mega stands for 10 to the 6th. So I'm going to write 4.5. Mega is 10 to the 6th meters. And then we're just going to put a times sign in there. Now we've written it in scientific notation. So the mega in megameter is just a shorthand way of writing times 10 to the 6 meters. Doing it the other way, looking at this one, 7.13 times 10 to the minus 9 liters is equivalent to how many nanoliters? Well, what does the prefix nano mean? 10 to the minus 9. Some of these have some sense in them. 9, nano, 90. So that means 10 to the minus 9. And so this question was set up to be simple. We take this times 10 to the minus 9, and instead of writing that, we write nano. 7.13, lowercase n, capital L. Any questions? So those are the base units: length, time, temperature, mass. There are also derived units. Derived units are combinations of other units. A rate or a speed is a combined unit. It's how far per unit time. So miles per hour or meters per second. Volume is also often a derived unit. If you take a unit of length and cube it, it becomes a unit volume. I'm sorry, a volume. No, I'm just messed up here. Yeah, that's supposed to be volume unit. I wondered why that looked strange yesterday. It's a volume unit. That's because if we have a cube, the volume is the length times the width times the height. If you measure all of those dimensions in centimeters and you plug them into this equation, you get a number, centimeter times centimeter times centimeter. That's centimeter to the third power, or centimeters cubed. That's a volume unit. Other common volume units are liter and milliliter, and these are usually used for liquids, and so they're more like gallon or fluid ounce in the English system. So here we have a big cube, and each side is 10 centimeters. So 10 centimeters this way, 10 centimeters this way, 10 centimeters this way. And they're asking how many small cubes that measure 1 centimeter on a side would be needed to make this big one. How many little blocks do you have to stick together? Well, each of these little blocks is 1 centimeter cubed. So if we know the volume of this big cube, we'd know how many of the little blocks we need. The other way to think of it in terms of numbers of blocks is, well, count how many across and how many high and how many deep. It's 10 on each side. So we get the volume equals 10 centimeters in length times 10 centimeters in width times 10 centimeters high. And we do the multiplication. 10 times 10 times 10 is 1,000. And the units come out centimeters cubed. This volume, 10 centimeters on a side, is equivalent to 1 liter. So this is equivalent to 1 liter. And this little guy is a milliliter. Milli means 1/1000th. This cube, we need 1,000 of them to make the big cube. This cube is 1/1000th the size of the big cube. So this right here is a relationship that students often overlook. And then forgetting about that will get you stumped on a unit conversion problem. A cubic centimeter, that little block, is the same as a milliliter. Milliliter is just a different name for the same unit. Okay? And in medicine, they call it something else. They call it cc. cc stands for cubic centimeter. Here are some other units and relationships. There's really only one on here that you need to memorize, and that's the relationship between inches and centimeters. The reason you need to memorize that is because we use it so frequently. I'm going to expect you to know that one. 1 inch is 2.54 centimeters. The rest of them, if you need them on a test, I'll give them to you. And then, of course, this one. You need this one. Another derived unit is for density. Density is the ratio of the mass of an object to its volume. So we say that density is mass divided by volume. And common units for liquids and solids are going to be grams per milliliter or grams per cubic centimeter. Remember, a milliliter and cubic centimeter are the same thing. They're just different names for the same thing. Density is a physical property that depends on the temperature of the object. It's usually not a strong temperature dependence, but the density of an object will change slightly with temperature. That's why when you see a table like this, the density of some common substances, they will often tell you what temperature these were measured at. Because if you're doing this at 100 degrees Celsius, the difference might be significant for what you're doing. But this just lists some of the densities. There's really only one on here that I want you to know. The density of liquid water is 1 gram per cubic centimeter. The rest of them, if you need a density, you go look it up. In some of the homework problems on Mastering Chemistry, you'll need a density. They're not going to give it to you. It'll look like there's a missing piece. The density will be given in the book somewhere. Go look it up. We talked about chemical versus physical properties. We can also take properties and divide them into groups called intensive and extensive. Intensive properties don't depend on how much stuff you have. Okay? So intensive properties are things like density, melting point, or color. If I take my raspberry lemonade here and I drink, what color is this? Kind of a pink color, right? And I drank some. Did the color change? No. The color of it doesn't depend on how much there is. If I had a gallon or a teaspoon, it'd be the same color. Density is an intensive property. It doesn't depend on how much you have. Extensive properties depend on how much substance you have. So the mass of an object. Imagine a big piece of wood. Okay, it has a length, it has a mass, it has a volume. If I cut the wood in half and look at one of the pieces, is the mass different? Sure it is. If you cut it exactly in half, the mass is half. What happened to the volume? Is the volume different? If I take a piece of wood and I cut it in half, does the volume change? Mm-hmm. Does the density change? No. The density doesn't change. Because density is mass divided by volume. Density is mass divided by volume. If I cut the mass in half and I cut the volume in half, that dividing in half cancels out. The density is the same. Calculating density. This is an example of a story problem, a word problem. When I was growing up, they called them story problems. That sounds more friendly than a word problem. There's a story here. A man receives a platinum ring from his fiancée. Before the wedding, he notices that the ring feels a little light for its size and decides to determine its density. He places the ring on a balance and finds that it has a mass of 3.15 grams. He then finds that the ring displaces 0.233 cubic centimeters of water. Is the ring made of platinum? So there's a story there. Do we need to know the stuff about his fiancée? No, we don't. It's just this background stuff. What's important in these problems are the numbers. You need to read the words, but don't get obsessed about the words. Go in and pull the numbers out. So you read through the problem all the way through. Then you go back and you find the numbers and you write those down. So 3.15, include the units. Always, always write the units. So we've got that, and we've got 0.233 cubic centimeters. Now, ring displacing that amount of water, that might not be obvious to you what that's telling you. One way to measure the volume of something is by how much water it displaces. I think we all know from experience that if you fill the bathtub up to the very top and then you get in, what's going to happen? The end result is your mom or dad gets mad at you. But the intermediate result is a bunch of water comes out. The amount of water that comes out is equal in volume to the amount of U that went in, the volume of U. So you can measure things by displacement. So this is telling us the volume of the ring, and this is telling us the mass. The units are a clue too, because we just learned that cubic centimeter is a unit of volume. We want to know if it's made out of platinum. Platinum always has the same density. And the other clue that you need to calculate density is it says that he decides to determine its density. So that's a clue. Well, maybe let's calculate the density, and that might help us with the question, is the ring made of platinum? Well, density equals the mass divided by the volume. So we're going to take the mass of the ring, 3.15 grams, and divide by the volume. This is called showing your work, and you should always do that. It doesn't take that long. 3.15 divided by 0.233 equals, my calculator says 3.5193133. The units on that would be grams per cubic centimeter. Anybody else get the same number? I screw up sometimes. I did it yesterday. If you're doing it and you're getting the wrong answer, no. If you're getting it and you're getting a different answer, ask me about it. Because I've had lectures where I did something wrong and nobody said anything. And then I posted on YouTube, and a month later, some wise guy from who knows where says, "You did your math wrong." So could you save me from the embarrassment of posting wrong stuff on the internet? So there's its density. How do we know if it's platinum? We need to look at the density of platinum. So we have to go look that up. Well, here, the density of platinum is listed down here at this bottom of the slide, 21.4. 13 and 21, those are pretty different. What do you think?
Is a ring made of mercury?
Yeah, his ring is made of mercury. The density of mercury is close to this. Now, obviously, it couldn't be mercury because mercury is a liquid and it wouldn't stay in ring form. But what that tells us is there might be some platinum in the ring, but there's also something much lighter, like maybe aluminum or something, so that the average density comes out to 13.5, but this is definitely not platinum. Any questions? And then here's the follow-up problem. The woman in this example is shocked. She wasn't being a cheapskate. She wasn't trying to pass something off on him. She got cheated at the jeweler. So she's shocked to find that the ring is fake. So she returns it and buys a new ring. New ring has a mass of 4.53 grams, volume of 0.212 cubic centimeters. Is this ring platinum? Well, since we just did a problem like this one should be a little easier. We know we need to calculate the density. So there's the mass. And the fact that this ring weighs a lot more is a good sign for this couple. So we're going to take the mass divided by the volume. And this time it comes out to 21.36792.453 grams per cubic centimeter. Now, is that exactly the same as the density of platinum? No, but it's really close. Anytime we make measurements, we're going to talk about this in a minute as well. Anytime we make measurements, there's some small errors. And so the fact that this is really close to the density of platinum says, yeah, I think this one is platinum. Any questions?